All atoms have isotopes. For example, uranium has 3 naturally occurring isotopes: uranium-234, 235, and 238. And when we use isotopes in nuclear transmutation reactions, we use an isotopic notation to report which specific isotope we are using. The formalism seen here reports the element along with the mass number and atomic number before that element's symbol. The upper left-hand corner represents the total sum of protons and neutrons, and the lower left represents the atomic number, or just the number of protons. Oftentimes we'll leave off the atomic number when writing nuclear reactions, as we have the symbol of the element present, and it is somewhat redundant to write 6, for example, when we're talking about carbon, because we know all carbon atoms have 6 protons. Well, not every isotope is stable, and what we have is unstable or radioactive isotopes. And these isotopes are decaying in one of several different ways. The most commonly encountered ones in nature are alpha decay, beta decay, and gamma. Alpha decay is a particle which has the same mass as a helium nucleus. It is the heaviest of the types of radiation in terms of mass, and it is probably the safest to be exposed to, although that's a relative term in terms of safety. The beta type of radiation is basically an electron. You have a negatively charged particle, has the mass of an electron, and for all intents and purposes, we consider it an electron. It is 100 times more penetrating than an alpha particle, meaning that beta radiation is a little more dangerous. It can actually go through your skin to damage living tissue. Alpha radiation basically hits the surface of your skin, and that's it. Nothing really else happens. Gamma radiation is actually just energy. It's pure energy in the form of a photon, and it can go through any and everything. It's 10,000 times more penetrating than an alpha particle, and the only way to protect yourself from gamma radiation is to put as many particles between you and the gamma radiation source as possible. Gamma radiation is always accompanied by alpha and beta decay. You're always going to get some amount of energy from a nuclear decay reaction. So we have our types of radioactive decay, alpha and beta, which produce particles. We have gamma emission, which is energy. Then we have what's known as positron emission and electron capture. Positron emission is simply an electron with a positive charge instead of a negative charge. Electron capture is where an electron is actually absorbed into the nucleus. We'll go into greater detail here now, starting with alpha decay. Here we have a decay of uranium-238 into thorium-234 by alpha decay. We can write either the Greek symbol alpha or represent the alpha with the symbol for helium. Both are equally correct. Notice that the numbers in the upper left-hand corner, that is uranium-238 on the reactant side, and the 234 from thorium and the 4 from helium also add up to 238. The numbers in the lower left-hand side do the same thing. Uranium is 92 protons, thorium is 90 plus another 2 for the helium particle equals 92. We must still obey the law of conservation of mass when balancing nuclear decay reactions. Beta decay works much the same way in terms of balancing it, except we have a -1 charge, so we have not a proton but an electron, which means that in this sort of decay, the mass of the nucleus remains the same, but the identity of the element changes. In fact, only alpha decay is responsible for the loss of mass in an atom. Everything else, whether it's beta decay or electron capture, sees the overall mass of the nucleus remain unchanged. Gamma emission is just represented with a gamma symbol. Positron emission is just the opposite of what we saw a minute ago, in that we have a positively charged particle with the mass of an electron. Electron capture is the only nuclear transformation reaction in which we have the subatomic particle as a reactant. Here we are actually slamming an electron into rubidium to produce krypton 81. Now, the last two are done synthetically or done in a lab, but alpha, beta, and gamma are always present in nature. So why aren't all the elements stable? Why do some isotopes stick around indefinitely and others don't? Well, it has to do with something known as the strong nuclear force. It is a force that exists essentially when protons and neutrons are in contact with each other. It's incredibly strong, and it overcomes the repulsive force of having multiple protons in close proximity. After all, we know like-charged particles repel each other. So in the nucleus, which has a lot of positively charged particles, it is the strong nuclear force that keeps the nucleus from flying apart. So why are some elements or isotopes on the periodic table radioactive and others aren't? Well, in order to understand that, we need to look at all isotopes of the elements on the periodic table, and then we can begin to understand why certain nuclear reactions or transmutations occur. What we see for the first 20 elements or so is that there's a 1-to-1 ratio of protons to neutrons for these elements. And that is, it doesn't take a lot of force to keep these nuclei together, but after 20 protons, it starts to become increasingly more difficult to keep these large number of positively charged particles together. And so what we see here on the right-hand side is all the known isotopes of the periodic table, and those are in either black or tan, but the stable ones are just in black. And so what we find is that there's this delta stability that appears to increase as we move across the periodic table, increasing the number of protons. The ratio starts off at 1-to-1, but by the time we're up to bismuth, we have to have approximately 1.5 neutrons for every proton. Above bismuth, it's impossible to keep the nucleus together. It's been hypothesized that there may be stable elements beyond bismuth, but none are known to date. So, where you are on the periodic table in terms of protons and neutrons will, in some instances, dictate what kind of radioactive decay you will undergo. Isotopes can have too many neutrons, or they can have too few neutrons, and that's the guiding factor in nuclear chemistry. So things that have too many neutrons transform by beta emission. That is, things above the black line undergo beta emission, and things below the black line undergo either electron capture or positron emission. Anything above bismuth undergoes alpha decay because it is simply too massive, and the nucleus needs to get rid of some of that positive charge. After all, alpha decay is the only type of radiation which causes the mass of the nucleus to change. So, here we go. Reasons why some isotopes are radioactive. We have too many neutrons, too few neutrons, or just too many protons and neutrons altogether.